So I try to be standing here. It's easy for me to show things because I believe the pointer would not. Oh, it does work here. Not so bad. So what I try to do today is to show you some practical examples of how phosphorus flame retardants work. So what I'm going to present today is summary of a lot of our work. So it will focus on what we have been doing over the years in my team, starting from my own PhD till Shuyu's PhD now, I would say. So I'm trying to cover different aspects of how phosphorus acts as a flame retardant by giving you some practical examples. Just a question for the audience. How many of you guys are not chemists? Not chemists, and you have absolutely no idea about chemistry? So I'll try to be very simple, I would say, because there are a lot of structures I'm going to show, but please don't be afraid. Just ask me if you have any question. I try to simplify things. Obviously, 1 hour is not enough to talk about everything, so I try to give you some insight. Okay, so the summary. It starts with some chemical structures. So don't be afraid. I will try to explain you all the way. So what I'm going to do is start with some basics. You guys have already heard about fire, flame retardants, how do they work, and how you design buildings, and how do you make them flame retardant. So what I'm trying to do here is trying to go very specific. How phosphorus as a flame retardant work, and how we can really design new flame retardant and by understanding how they behave, I would say. Okay. So what I'm trying to do here, phosphorus, as you have already heard, probably the past few days, work in different ways. Okay. It can work in the gas phase. It can also work in the condensed phase. Okay. I'm gonna give you some examples. So when it works in the condensed phase, I will also define what it means by condensed phase. How by designing different molecules, you are able to tune the way it will work. Okay? So what I'm trying to always do over the years is try to design molecules which are more efficient. Okay? Not only are we understanding how they behave, but also able to design molecules which are able to perform in a certain way. So that's what we're trying to do. So if you see here, the first part of my talk will focus mostly on condensed phase mode of action. Okay, where I'm trying to work on these structures here. I'm going to show you some examples how by designing molecules with different groups on the phosphorus, we are able to make them more efficient. Okay, and then going down. Okay, so the first part will be more showing an example on phosphoryl molecules or phosphoryl group. And then going down further, you have functional groups which are attached to this X here. By changing the group here, I'm able to tune the activity of the phosphorus compound. And then later on, I'm going to talk a little bit about the size. Small size, bigger size, which of them are more suitable for condensed phase. Okay? So I'm going to cover a lot of these aspects, I would say, of how phosphorus molecules can be tuned. And then later on, I'm going to move to the second part of my presentation. It's all about gas phase flame retardant. Okay, and what we have been trying to do to understand how these groups of the phosphorus help them be better gas phase flame retardant. Okay, and then at the end, I'm going to talk about how to evaluate this gas phase activity. It's very challenging, I would say. We have spent a lot of time on trying to understand how this gas phase activity of flame retardants can be understood. Obviously, what I'm trying to present is my opinion, and also is my group's opinion. I believe you guys also have your own opinion. All the other experts who are publishing in this area also have their own opinion, and I believe by bringing the opinions together, we will come up with the final agreement, I would say. And it's a long way to really know exactly how molecules behave in fire. Okay, it's quite complex, I would say. So some of you already know me, I would say. Those of you who don't know me, actually we come from a small place known as Gallen. It's northeast of Switzerland, and I think we have been working on flame retardant in EMPA for almost, I believe, 14 years now. And out of these 14 years, eight of mine are also included, I would say. They already started working before I joined EMPA, I would say. So we belong to the Swiss federal government. It's a material science institute. And as a part of this material science, we also have a lab which is focused on developing fibers. Okay, so that's advanced fibers. But in the fibers group, we are also developing a lot of additives for fibers, and flame retardant is just one additive we work with. Obviously, fiber is just one substrate. We also work with many other substrates. So I'm working with wood. I'm working with engineering plastics, polyurethane foams, the different kinds of materials, I would say. I'm trying to develop, and metals, I would say. Phosphorus can also be used to develop metal coatings. So obviously, the research is quite diverse, what we are trying to do, listed here. But the final goal is to develop solutions which are commercially viable. Okay, so most of my research are funded by industrial projects. That means at the end of the project, I need to have certain products we need to come up with, and we are quite successful in bringing our ideas to the market in the last 8 or 9 years, I would say. Obviously, I'm not going to talk about commercial things. I'm going to talk more about mechanisms of trying to give you guys an idea about how phosphorus behaves. And just an example here, I like this picture very much because it gives you a lot of information. You can see there is a voluminous chart. So I believe our previous speaker was talking about intumescent additives. And you can see the char which is at the background is because of the intumescent nature. And then you can see the bright flame, the yellow flame, and the blue flame which is on top of this material here. The reason why the colors are different is because the chemistry is different. Okay? The chemistry here is quite different to the chemistry here. And if you have a phosphorus flame retardant, if you try to burn a material containing phosphorus, you see a bright flame, a yellow bright flame, and that's characteristic of this flame here. So this is a new additive we have developed, which is doing both gas and condensed phase at the same time. So when you put flame on it, it forms a char, and then it also releases phosphoryl radicals, which act in the gas phase, and you can see this nice brilliant color, I would say. Okay, so I'm not going to talk about this additive today, but what happens in fire? So we have been talking about this, and I tried to give you an example of a real example of what really happens in fire. And these are fibers, polyester fibers, which have flame retardant inside. And what happens is when you have a polymer exposed to fire, you have fuel being generated. So these are the areas you can see some bubbles being formed on the surface of the fiber when you put heat on it. And these bubbles are actually volatile gases. And then it combines with oxygen somewhere on the surface. Okay? And then you release a lot of, there is an oxidation happening, and there is a lot of heat and light being produced. Okay? The heat is fed back into the system. And the whole cycle goes on forever till everything burns down, or you have a material which is able to self-extinguish. Okay? So what is really nice about this picture is you can see different aspects of the combustion process. Okay? Something what is quite interesting at the end of the process is dripping. Okay? If you have a thermoplastic material, you will see dripping happening also. Okay? It will melt, the material will melt and drip. And all the flame retardant action of phosphorus additives which is present in this fiber is clearly visible here. Okay? You can see here the black stuff, that's the char, okay? Which is because of the additive itself. And then you can see the melting behavior, which is enhanced by the fact that the phosphorus which is present in the polymer breaks it apart, or it helps in hydrolyzing the material, in this case it's polyester, into smaller fragments, which drips away. Okay? And that is another way the flame retardant actually works. And then you can see the bright yellow flame. The bright yellow flame is actually the phosphoryl radical, okay, an axonophosphoryl radical. Okay, so there are certain things you can see which is clearly indicating how polymers decompose, and if the flame retardant is there, what is happening, I would say. So let's go into specific of how phosphorus acts as a flame retardant. To me, I'm trying to simplify things here. Okay, so there are other ways the phosphorus may have worked, but primarily it is condensed phase, where the additive itself reacts with the polymer or other additive present in the polymer, and you form a barrier, okay, which is like a carbon residue, okay, on the surface, which you saw in the previous picture, huh? And that insulates the material from further damage, okay. But what actually happens in gas phase is you have radicals being formed from polymer which is decomposing, the phosphoryl radical, and other phosphorus species which are formed actually interact with each other. Okay, so I will go more in detail later on, but at this moment, just keep in mind that the radicals which are formed from decomposition of the polymer, which is mostly the hydrogen and hydroxyl radicals, they are quenched somehow, or they are recombined. I will show you some specific equations later on. And then, because the phosphoryl is there, it prevents the oxidation of these polymer radicals, okay? And prevents the oxidation and prevents the burning, okay? And now phosphorus, I would say, it's quite interesting element, I would say. It was discovered by, it's a German chemist, I would say. It's an alchemist, I would say, Henny Grant. And he actually was trying to find, I would say, ways to make precious metals. Huh? So at that time, alchemists were mostly interested to find how to make gold, how to produce precious metal. And he ended up discovering by accident phosphorus. Okay, so what he was trying to do is he collected the urine. I don't know how he came up with the idea. He collected his own urine and urine from other people, and then he removed all the liquid from the urine, ended up with the material which is at the end known as phosphorus, because it glows in the dark. That's the way it is named. So he discovered it, and interesting, phosphorus. If you look at the periodic table, probably everyone has seen this periodic table once in their life, I would say. You can see it is situated in a very nice place. Okay, so it has it has an electronic configuration of 3s2, 3p3 in the valence cell. So that means it has 5 electrons in the valence cell. It needs 3 more electrons to finish its octet, but it actually, due to hybridization, it can have 5 more electrons in total, I would say. And it loves oxygen. The fact that it is very, the electronegativity is very low, it is able to interact with more electronegative elements. And that is one of the reasons why phosphorus is very, very interesting as a flame retardant, because the electronegativity is quite low. So it loves oxygen, so the moment it sees oxygen somewhere, it likes to bind to oxygen. Okay? Phosphorus as such is not really a good flame retardant by itself. However, there are different forms of phosphorus. There are almost 10 allotropes of phosphorus. It's purely phosphorus, but the way they are bonded to each other leads to different kinds of phosphorus, I would say, allotropes. Okay? So you can see this one here is white phosphorus or yellow phosphorus, because it's a tetrahedral structure. And because it's a very strained ring, it's very reactive. Okay, so white phosphorus, if you have done experiments in chemistry, if you put it outside in air, I would say it immediately oxidizes and burns. It's very dangerous. You should not play with it, I would say. However, you can see there are other forms of phosphorus, a red phosphorus, which is more or less like a polymer kind of structure, I would say. It's much more stable, because the ring is not so, it's not in in a cage structure, it's a little bit lenient, I would say. So it is less reactive. And red phosphorus is an excellent flame retardant. If you know, in industry, red phosphorus is used as an additive for engineering plastics. It's quite common. It's really, really effective. However, it could be quite toxic also. If you burn it, you release phosphine as a gas, which is not really interesting. Or you process it, it's really toxic also. However, it is still used in industry. It's an excellent flame retardant, especially for polyamides. Okay? And you need only like 5 or 6% to really have a very good flame retardancy. Okay, so let's move to the first part of my talk, where I'm going to talk about condensed phase flame retardant action. And this part of the study has been carried out when I was doing my PhD, and later on in my career in EMPA, early career in EMPA, where we were mostly focused on cellulose as a substrate. Okay, so what we tried to do in the beginning, I would say, when I actually was a PhD student, I was looking at why some phosphorus molecules are really very interesting. Okay, if you look at this structure here, it's a phosphonate. Okay, because it has a PC, PO, PO bond. Okay, it's a phosphonate species. It is the most effective flame retardant for cotton. Okay, if you buy a flame retardant cotton, it is very likely that it contains this molecule because it can react with cellulose. Okay, and it is very, very effective. However, because of this formaldehyde, which is linked to this molecule, it is there's always a need to replace it. Okay, and in the beginning of my PhD, I was looking at alternatives. If I can find additives which are which can replace this guy here. Okay, it's very efficient. It's still being used in industry, in textile industry. Okay, so what I was trying to understand is why is this guy very effective? Because there was no literature on about his efficacy. So what I did was I compared it with similar molecules, molecular weight more or less same, but the structure is a little bit different. You can see this is a phosphonate, this is a phosphoramidate, and this is a phosphate. Okay, I tried to keep the molecular weight constant. If you can see, the LOI values are different phosphorus content, I would say. You can see HDPP, which is this guy here, is having higher LOI values at similar phosphorus content. That means it's a better flame retardant. Obviously, it is a better flame retardant. And the reason why people say it works in the condensed phase is if you look at these values here, TGA values. Okay, when you take a material, okay, you put it in a heater, I would say, there will be a weight loss. You see some weight loss. Okay, and the way to look at condensed phase activity is looking at how much charge is left after the test. If you have a higher amount of charge left, there is the more likeliness that you have better condensed phase activity. Okay? So if you look at this TGA data here, you can see this molecule here, HDPP, which is this guy here, has the highest charge content at the higher temperature. Okay? Which clearly indicates that the activity is that the condensed phase activity is the highest. If you carefully look at the TGA data, you can also see, depending on the structure of the additive, you have different decomposition temperature. Okay? And phosphorus flame retardant, if they work in condensed phase, they tend to catalyze the decomposition of a material to happen at a lower temperature. So if you look at this TGA curve A, that's actually a cellulose, a pure cellulose. It decomposes at a very high temperature. But when you have an additive which works in condensed phase, it catalyzes it to decompose at a lower temperature, which is actually not bad, because it changes the pathway of how cellulose decomposes. And it leads to intermediates which are thermally more stable at higher temperature. Although it is decomposing at lower temperature, but it is actually producing charge which is thermally more stable. Okay? So that's key. So if you want to develop a condensed phase flame retardant, you want to have the char content as much as high as possible, and hopefully you can look at the curve and you can tell, okay, the catalysis is happening because it's decomposing at low temperature. I will explain you why catalyzing decomposition at the low temperature is interesting later. Okay. So what really we found out is this molecule HDPP, when you heat it up, it breaks down to release these acidic species. Okay, something I don't want to go into detail how we found that, but we found out that we are ending up having these acidic phosphates being formed from that molecule quite efficiently. Okay, and that was the key to understanding the whole puzzle, I would say. Okay, why this molecule is interesting. You don't have to go into details. What I want to say here is, look at the species here. This is the key species. If you are able to form this acidic intermediate, you are able to change the pyrolysis pathway of cellulose. Okay? So what is happening is, if you have an acid with the cellulose or any hydroxyl group, you dehydrate the system and you end up forming char. Okay? Rather than forming flammable gases. Okay? So that is the key. Okay? So that's how. So by having a structure which is able to produce more acid, you're able to make it work as a better flame retardant. Okay. Later on, we moved on. I would say when I joined EPA, I actually looked into why certain structures are more efficient and how I can even make these structures better. So one of the first molecules we were looking at are these phosphoramidates. If you look, the phosphoramidates are species with phosphorus directly linked to nitrogen. Okay, so you just need to look at the nitrogen right there. And then what we were trying to understand is why that molecule is also a good flame retardant, okay, compared to different molecules. And by changing the substituent on nitrogen, if we can change the way they can work efficiently. So what we were trying to do is, we had a phosphate, this guy here, and we compared it to different kinds of phosphoramidates. You can see this is the simplest phosphoramidate, and by changing the alkyl group on the nitrogen, we are able to produce different kinds. And what is more interesting is this guy here, which is with a hydroxyl group at the end. And if you look at the TGA data, too much information here, but just focus on these two molecules here. This is this guy here, DEPA, and then the other one is PHEDE. You can see the LOI value and the char content are the highest for these two molecules. Okay, and all the phosphoramidates had better flame retardancy compared to the phosphate. Okay, that's something we also have to see here. And I was trying to explain why all phosphoramidates are better than this guy here as a flame retardant. If you look at the char content compared to phosphate, all phosphoramidates had higher char content. So if you are able to produce a lot of char, you are able to have a better flame retardant effect. Okay, and you can see the same thing here in the TGA experiments. We observed the same thing. A phosphoramidate always had a better, I would say, higher char content compared to a phosphate, okay, which is this guy here. And you can see the catalytic activity of the additive, which changes the decomposition temperature, is much more efficient for phosphoramidates. Whereas the phosphate here is decomposing at a much higher temperature, which is very close to that of a normal cellulose, I would say. So by changing the decomposition characteristic, you're able to make a more efficient thermally stable char. Okay. What also we were trying to understand was the use of pyrolysis combustion flow calorimeter, or MCC. I believe you might have heard about this technique. So basically you take a milligram quantity of material and you heat up, at a very high heating rate, and then you see the heat release of the material. I'm just giving you an example here. So what you did basically was you take a material, you heat up very high, very high, I would say, with a high heating rate, and then you observe what is the heat release rate. Okay. So for example, here, which is a cellulose, decomposes and produces a lot of heat. If you have a flame retardant, depending on its efficacy, you can have a smaller heat curve or you can have a bigger heat curve. Okay? And the smaller the curve, the heat release rate curve, or heat release rate, the better flame retardant efficacy you have. Okay? So by designing different flame retardant, we are able to screen the heat release rate, and then we are able to say which of these additives are more efficient. Okay? This is just an example. These are not the real curves for the previous data which I showed. So if you look at the TGA data, the heat release rate data, for the additive which is more efficient has a lower heat release rate, I would say, if you can look at this data. And also the temperature at which you see this peak, okay? The temperature, the lower the temperature, the better it is, okay, for a phosphorus flame retardant. I will explain you why. We also try to understand what are the gases being formed. Okay, so when you heat up a material, when you heat up cellulose, you end up having several kinds of gases being formed. If you look at carbon dioxide, carbon monoxide, water, and then some carbonate compounds. And when you have a flame retardant molecule inside, these gases which are formed changes. The intensity of gases which are formed changes. And it gives you an idea about the chemistry which is occurring in the condensed phase. Okay? For example, if you look at these peaks here, okay, this is the amount of water which is being formed when you have a flame retardant there. So when you have a phosphorus flame retardant in cellulose, the flame retardant reacts with cellulose, it dehydrates the material, releases a lot of water, and what we are trying to do here is to measure the amount of water being released through FTIR data, I would say, okay? And you can see an efficient flame retardant is able to do this dehydration at a lower temperature. You can see for this molecule here, compared to normal, I would say, cellulose, and the peak. If you integrate the peak, the amount of water which is being produced is also quite high. Okay, so it gives you an idea about the condensed phase activity. Okay, so without going more into detail, you can see the peaks are very similar to TGA curves here. Okay, so basically the peak decomposition temperature in TGA matches the peak water releasing curves. Okay, so you need to always look at two different data at the same time to understand what's going on, I would say. Okay? So, ignore that, I would say. So, again, going back, I would say, what is really the condensed phase? So, if you have cellulose, when you heat up cellulose, if there is nothing happening, there are two reactions happening at the same time. Levoglucosan is a species which is formed, which is responsible for really the heat release, because this is the flammable component. And if you have dehydration happening, you end up having char formation. This happens at a lower temperature compared to this reaction. Okay? So we need to have a flame retardant which can reduce this temperature, I would say, at least this reaction happens. We prevent the formation of levoglucosan, you're able to do a better condensed phase activities. Okay? So that's the key, I would say. In order for cellulose not to release a lot of levoglucosan, you need to have this guy, or this reaction happening more, I would say. And that is actually done by all phosphorus flame retardant. Okay? And depending on the structure of the phosphorus compound, some of them have better efficacy compared to others, I would say. Okay? So the key is to be able to form from different flame retardant acidic species. Okay? because acidic species are needed to get this reaction done, which is dehydration. Okay, and different phosphorus flame retardants have different ability to produce acidic intermediates. Okay, and that's the key, I would say. We came to the conclusion in our research that a hydroxyl terminating phosphoramidate is quite efficient in releasing acidic species, I would say, which is these guys here, these acidic species, I would say, which is able to dehydrate cellulose, and that is the we are finding. So by designing the structure of a molecule, you are able to produce acids which are able to dehydrate cellulose in a better way. We further moved on and we said, okay, now we know by designing phosphorus with different substituents, we are able to produce acids to a certain extent. But does size matter? If you have a bigger molecule, if you have a smaller molecule, are you able to have better flame retardant effect? So what we try to do here, you can see, these are analogous compounds. The difference being the one at the left, the molecules on the left are smaller compared to the molecules on the right. Okay, they're exactly the same molecules. It's just the size is a little bit bigger on the right. Okay, so if you look at we developed these additives, we put it on cellulose, and we looked at the limiting oxygen index. The smaller molecule, the bigger molecule. You can see the smaller molecules always had higher LOI values. I believe you have probably heard what is a limiting oxygen index. It's the amount of oxygen needed to sustain burning, I would say. So more or less minimum amount of oxygen. So you can see higher the number, the better is the efficacy. So you can see, if you look at the small molecule, bigger molecule, the small molecules always had the higher LOI values and higher char content, even at the same phosphorus content. So you can clearly say, if you have a smaller flame retardant, it is quite efficient in doing the condensed phase compared to a bigger molecule. And this is something which a non-chemist can also understand. So what we are trying to propose here is, if you have a substrate, if you have a smaller molecule, the smaller molecules are able to interact with the substrate quite efficiently because it is in intimate contact with the polymer compared to the bigger molecules. So the bigger molecules are not really touching the polymer. For a condensed phase to happen, the phosphorus compound has to be really in contact with the polymer. They need to see each other. If they don't see each other, you do not see the reaction happening. So the smaller the molecule, the more easy it is to react to the cellulose. So you can see bigger molecules are sitting idle on the surface and they just volatilize rather than reacting with the cellulose. Okay? So at the end, I would say, I talked a lot about the chemistry, I would say. But just summarizing it, the condensed phase activity of phosphorus with cellulose mostly depend on the chemical interaction of the phosphorus with the substrate. That means the phosphorus has to react with the substrate. Somehow there has to be some kind of reaction happening. Okay? And it's mostly, the reaction leads to catalytic decomposition. Catalytic decomposition doesn't mean that you're producing more flammable gas. What you're trying to produce is non-flammable gas and a char which is able to shield the further decomposition. Okay? So factors which affect the condensed phase activity of phosphorus compound are like its affinity to the substrate. If a phosphorus compound do not like the material, it would not do the condensed phase activity. It has to like the material. Okay, it's very important. They need to have the same affinity. If you have a very hydrophobic material, a hydrophilic phosphorus flame retardant, they would not interact. Okay, they would not like each other, and then you do not see the condensed phase activity. Okay. So the chemistry around the phosphoryl, I already showed you, phosphonate, phosphoramidate, phosphate, also has a big role to play. Okay, so at the end, you really need to decide what you want to put around the phosphorus to have the best effect, I would say. The shape is quite important. A smaller phosphorus compound is quite efficient because it's able to see the polymer better, I would say. And liquids and solids are also very important. Sometimes liquids are easy for application, but they are not very efficient because if they are not bound to cellulose or to substrate, they will just volatilize, okay, at a lower temperature, and you do not see the reaction between the polymer and the liquid. However, if you have a solid, the solid doesn't volatilize, it remains in the substrate, so you have a better interaction, okay? Obviously, there are several tools I would say you can use. The most easy tool is to just burn and see how much char is left, or just heat up the material and see how much char is being formed. Higher the char being formed, the more is the condensed phase activity. In PCFC, lower the heat release rate, the better is the condensed phase activity. And higher the char in PCFC, the better is the condensed phase activity. So you can use different tools. I believe people have already talked about it. I don't want to go into details. Now I move to the second part of my talk, which is more concerned with the gas phase activity. We were working in ENCOP for a long time on cellulose as a substrate. Okay, we were trying to develop flame retardant for cellulose, and that's why I came up with all these nice chemistry, trying to understand what's happening to the cellulose. But at one point we did a project on polyurethane foams, okay, where we realized that we need to really understand how additives work in polyurethane foams. So it was a big project. We ended up in successful commercialization of a nice new flame retardant. We patented the molecules. It's environmentally friendly additive, and it's going to be in the market very soon. So it's a nice project, but we learned a lot in this process, I would say. First of all, polyurethane compared to cellulose has no free hydroxyl group. You basically have no hydroxyl group, or the chemistry itself is different, I would say. Huh? And the form is quite different. It's a very porous material. Okay, and we were working with open cell structures and soft polyurethane foams, I would say. So we learned a lot in this project, and due to this, we are able to come up with some idea about how flame retardants work in the gas phase. So you probably joined us in this project. It was his first project, and we were trying to understand if we can have a better flame retardant. If you look at the polyurethane industry, they usually use chlorophosphates as flame retardant. It's very cheap, around 2 to 3 euros per kilo. Depending on the chemistry of chlorophosphates, they are quite toxic, I would say. Some of them are already banned. And thus, our goal was to develop additives which are replacement of chlorophosphate. By the way, the largest or the biggest phosphorus flame retardant which is produced and sold in the market are still the chlorophosphates. Okay, so they are the largest volume-wise. It's very cheap. Okay, when we wanted to replace those chlorophosphates because they are toxic, in the beginning we went into a study where we like to understand, by changing the chemistry of phosphorus compounds, are we able to design better flame retardant or not? You can see there are 3 different classes of compounds we made: phosphates, phosphoramidate, and phosphonates. As usual, phosphates have all oxygen connected to the phosphorus, phosphoramidate nitrogen connected additionally, and then phosphonates a carbon connected. Okay, so that's the difference. You just have, as a non-chemist, you just have to know the difference. Okay, but you can see within the same class we also have different structures. You can see you have a propyl group, a allyl group, and you are having a benzyl group. Okay, so there are 3 different groups, and by trying to change the substituent on the phosphorus, we are able to design or understand its flame retardancy or tune the flame retardancy. So what we found out in the project these guys here, phosphates, are probably the worst flame retardant for polyurethane foams. Okay? And then we found out these phosphoramidates and phosphonates are better than the phosphates. Okay? And I don't have to go into details, but there is a reason why we took these special groups, I would say. You can see the alleles and the benzyls are very good leaving group as radicals. So when you heat up a material, additive, if you have an allele group or a benzyl group, they cleave off because of the radical stabilizing effect of the allele and benzylic radicals. Okay? And that was the idea. So if you have something which splits quite easily, goes away, you end up having a phosphoryl radical more efficiently. So that was the goal. So we made some foams. As usual, foams are made up of polyols and isocyanate. You just combine them. And we had a density which we were around 43. And we were comparing it to this guy here, propyl phosphate. This is probably one of the largest flame retardant which is sold in the market as a phosphorus, okay, compound. But there are studies which show that this is toxic, I would say, to a certain extent. Okay? So, in the beginning, so we had this same series of molecules. We came up with the fact that the phosphonates and the phosphoramidates were better than the phosphates. I'm not going to show you the details, but look at just one comparison. Okay, you can see phosphate in the middle, and the ratings in the middle are the worst rating compared to the ratings on the side for phosphonates and phosphoramidates, I would say. So it's a UL 94 test, huh? So instead of having a vertical test, it's a horizontal test. So you put the flame in a horizontal material, I would say, which is a foam, and you look at how it burns, okay? If it drips, if it burns the cellulose, then you actually have no rating. So the highest classification one can achieve is HF1. That means the foam is able to stop burning within the first within the first 2 seconds of removing the flame, and it doesn't drip any flammable I would say drips. That means the cotton underneath is not burning. So the edge is HF1 rating. Okay, that's the best rating you can achieve. Okay, in building industry, it is quite common to have this kind of I would say rating. So you can see HBF, which is no classification. Everything burns. Okay, so you can see that you have phosphonates and phosphoramidates both achieving HF1. So this guy here is not achieving the HF1 rating. It's just barely, not even fulfilling the norm, I would say. And so our question was, why do you see this difference? This is something we have always been asking. And what we also observed was, when you heat up these polyurethane foams in a TGA, you don't see any increase in char content. That means, obviously, there is no condensed phase activity. Okay? So, which is presented here. If you look at the flame retardant, which is put in the polyurethane foam, you can see, compared to cellulose, you remember cellulose always had a char of 30-40% depending on what phosphorus additive was there. Here, you don't see any char being formed. So what is actually happening to the phosphorus? Huh? You also see there is no catalytic decomposition. It's more or less following the same path as a virgin polymer, okay? A virgin PU form. So that means the additive is doing something, because we see the fire results are good, but you don't see any char being formed, you don't see any catalytic decomposition. That means the additive has to work in the gas phase, okay? And that is the conclusion we came up with. For sure, the additive is working as a flame retardant, but it is not working in the gas phase. And we tried to explain why the phosphate molecules are not as efficient compared to the phosphoramidates and phosphonates. It's a very crude way of trying to explain the gas phase mechanism. So what we did was, we took the additive, we just put it in a mass spec, okay? And in a mass spec, what you do is you break apart the molecules. When you break it apart, you end up having different fragments. Okay, the key fragment you look at is the PO fragment, which is supposed to do the flame retardant action. We found out for phosphoramidate and phosphonate, it was very efficient in getting these PO species, quite efficient in the fragmentation pattern. However, in case of phosphate, we also saw an additional pathway which was more or less like an acid. If you look at the phosphoric acid, it is very similar in structure here, I would say, what I'm trying to show. So the key difference was the fragmentation pattern of phosphate compared to a phosphoramidate and phosphonate were quite different. And we tried to explain the gas phase activity by formation of PO radical and easy formation of PO radical, and there are no other pathways leading to formation of the condensed phase additive object. So when you have a flame retardant which releases phosphoric acid, it tends to stay in the substrate, doesn't go in the gas phase. Okay, the phosphate tend to give this phosphoric acid quite easily compared to the phosphoramide, and that's why it was not a good flame retardant. Okay, so just to summarize, I would say the first part I would say of this gas phase activity. This is if you are forming phosphoric acid from a flame retardant, you tend to have a condensed phase action. It's very difficult, but however, the condensed phase action is not efficient because a polymer which doesn't have any hydroxyl group is not able to dehydrate. Okay, so you have to understand you cannot expect a phosphorus flame retardant to work in condensed phase if there is no dehydration possibility. Okay, a polyurethane by itself has no free hydroxyl group, so it is not being able to dehydrate in presence of phosphorus. So obviously it has to work in the flame retardant has to work in the gas phase. And the fact that PC and PN bonds are easy to cleave, you end up having more PO radicals, I would say. Okay, and that's what we try to prove in this work, I would say. And then obviously we were not very happy with our explanation as to what really is the gas phase. Okay, we looked up in the literature and we found there are different ways you can actually quantify or qualify gas phase activity, I would say. And you can see the top three on the listed here are the conventional techniques, okay, which people are using to quantify the gas phase activity. I believe Professor Cuesta is going to talk about MCC more in detail, how they use to quantify. Quantify means they're able to differentiate between structure. One has better efficacy than the other, but why is the question we are trying to answer. Why one structure is better in doing gas phase activity than the other is something which cannot be answered using these three techniques, I would say. Obviously you have to there are some ways to look at the chemistry by combining FTIR. I believe you combine FTIR to look at the species, but you still cannot see the species which are being formed, the real species which are formed when a phosphorus molecule breaks apart, because it is very, very unstable. These species are quite unstable, and these techniques have long pathways before you reach a detector, so you really don't see. You do not get a snapshot of the species which are formed. That's why these techniques here listed below are more suitable. I'm not going to go into detail of these techniques. What I'm going to talk about is this technique here, VUV iPeptico. Okay, this is a new technique which we are trying to use to understand how phosphorus compounds work in the gas phase. I'm going to explain you why this technique is quite interesting, I would say. Let's see what is actually the real gas phase activity. I didn't explain till now what really is the gas phase activity. So, if you have a polymer, when it breaks down, it releases volatiles. These volatiles are small fragments of polymer. Okay, they further break down to release the H and OH radical. In a combustion process, the oxidation of H and OH species are the most, it produces, these are the key, I would say, energy releasing species. Okay? So if you're able to prevent the oxidation of H and OH somehow, you are able to prevent the whole combustion cycle, or retard it, I would say. So what is known now, till now, is if you have species like these, phosphoryl species, they're able to do all these recombination reactions. So what basically you're doing is you're combining a hydrogen radical with other hydrogen radical, you end up having a hydrogen, which prevents the oxidation. So you end up having water. So you actually recombine these radicals, the key radicals. When you combine them, you actually prevent the oxidation and prevent the heat being formed, I would say. Okay? And this is quite effectively done by all these people. This is known in literature. Okay? You can find tons of literature out there. But all these literature data are done on, I would say, a premix flame. A lot of these experiments are premix flame. But if you look at the polymer, when it burns, so it actually burns by two-stage theory. So first is you have volatilization and then you have combustion. And in a flame, the oxygen, when a polymer burns, the oxygen is diffusing from outside in. So the top of the polymer, where the decomposition is happening, doesn't see a lot of oxygen. Okay? So the chemistry of the flame in a premix flame, so most of the experiments are done using premix conditions. That means they take the fuel, they take the oxidizer, they mix them together, and they look at what species are formed. But in a real flame or a real polymer burning, the situation is different. So it is a diffusion flame. So oxygen is diffusing into the flame where it looks, where it finds or meets the species which are formed. So at the surface of the polymer, you basically, at this surface, you basically have no oxygen. So the chemistry of pyrolysis here, or chemistry of thermolysis here, is quite different to the chemistry here. Okay? So that's something one has to understand. That's something, it's quite important when you try to understand the mechanism of flame retardant. Okay? And that's what we are trying to also do. So, few years ago, we came up with a nice technique. We call it iPepico, I would say VUV iPepico. It's a technique where we are able to take radiation of a synchrotron. So a synchrotron is a source of energy. What you do is you move electrons at a very high speed in a circular path, and when you move it in a circular path, when they are bending all the time, it's releasing energy. And you take that energy, which is in form of photon, and you use that energy to ionize species. Okay? And that we do using this unique setup we have in PSI. So basically you take the energy from the synchrotron and then you pass it through the ionization chamber. But before this chamber, it's very easy to understand this way here. What we are trying to do is we are trying to pyrolyze or oxidize material, I would say, and then we make a molecular beam. So what is a molecular beam? A molecular beam is when you go from, when you actually expand the material or the volume so that when species are breaking apart, they don't interact with other species. Okay? So our key is when there are things which are breaking apart here in the pyrolyzer, we are able to freeze them by making a molecular beam. Okay? So that you do not see secondary reaction. And that's the key. We want to understand what is being formed at the point when a molecule sees heat, I would say. Okay? Then you make a molecular beam and then you do a VUV photoionization. So if you take the synchrotron radiation, you have different forms of energy you can, or photons you can get. Okay? We only take the VUV part. The fact that this energy is very intense and we are able to accurately control the energy of these photons, we are able to tune the ionization of the species which are formed here. So very accurately. That is the key. Okay? And then what we are trying to do is we are able to detect the mass. So when you have when a molecule sees energy, it splits apart. Okay, it splits apart into a positive charge and a negative electron. Okay, and then we are able to see the ions, and we are also able to see the electrons at the same time. That's the key to this technique. Okay, so it's a nice illustration from Shiyu. I would say you probably have already seen that. So it's the energy we take from the synchrotron. We pyrolyze the species here, or we heat up the species. We end up having molecules coming out from this end, the nozzle here. That's actually a reactor. And then when the species come out, you actually ionize, you make a molecular beam and then ionize it. The principle is right here. See? So you have the photon energy, and you have the fragment which is being formed from the decomposition of the phosphorus compound or any other compound. And what happens is when it sees energy, it splits up into two parts, a positive part and electron. And we are able to see this molecule, we are able to see this part using a time of flight mass spec. Okay? We can really observe this. And what is really nice is we are able to see the energy of the electron. Okay? And you know that the threshold photoionizing potential of each species is unique to its chemistry. Okay? So by mapping the electron energy, we can accurately say what species are being formed in this pyrolysis experiment. So you can see that's the mass spec data here. You see different masses being formed at different temperatures. But you also see there's a threshold photoelectron spectrum, okay, which is very specific for each species which are formed in a thermal decomposition process. Okay? And then by comparing both of them, we can come up with a nice mechanism. Okay? So you can see at different temperature, you have different species we are formed. Okay? So what we do is, in case of DMNP, we actually see a lot of these fragments which are formed. Some of them are already known. We know. Okay? 15 is a metal radical. We know it's quite easy to say. But some of the species, 47 is PO, we know very well. Okay? But some of them we don't know. Okay? So how do we say what are these species which are formed? So it takes a lot of intuition, a lot of calculation, some molecular modeling to come up with the real species which are formed. So how do we do it, I would say? Okay? These are for the phosphoramidates, I would say. A lot of different species are formed. Very interesting PN species which are formed. You don't have to go into details, I would say. What is quite interesting is we also collect the energy diagram of the electrons which are being ejected. Now these are the plot, I would say. So what we try to do is we compare the experimental value to the simulated value. If there is a match, well, we have to do a lot of calculation. If there's a match, then we can clearly say this is the species which are formed. Okay? And it takes a lot of work. I would say I think few months just to analyze the data to be able to come up with these kind of patterns or this kind of fragmentation, I would say. Okay? So what we are not trying to show here is there's a lot of effort gone into calculating the pathway. Okay? How do you do that? We do molecular modeling, I would say. So we know which species are being formed. We just have to draw the transition state. And to do the transition state, you need to do molecular modeling, I would say. We do all this modeling, we try to fit the experimental data to model, and finally we come up with this pathways. Okay? So you can see DMNP, which has never been, I would say, proposed, we published already. In the first stage, splits off releasing formaldehyde or methanol. Okay? End up having a PO at the top. It says PO here. But before it forms PO, it forms various isomers. These isomers, we are able to really detect these isomers and really say, okay, these isomers are the source for PO radical formation. So what I'm trying to say here is if we can find a nice molecules which are able to produce pure radical much more efficiently. By studying the energy diagram, we are able to design better flame retardants. Okay? So what we are trying to do here is really, which nobody else has done till now, is able to find all the fragments which leads to this pure radical being formed. And that's what we are trying to do actually. Okay, the chemistry, I would say. So I showed you an example of DMMP, which is a little bit more simple compared to what we see here. It's crazy. How many species are being formed? I think it took you 6 months to come up with only a part of this, I would say. There are several, I would say, energy diagrams we come up with. So don't be worried about too many things going on. But you can see these are the important species which you see them marked in red are quite interesting, which has never been shown as flame retardants. Like PN itself has never been shown being formed in a flame. But we have shown that PN, P triple bond N is also formed. But what is its role? We don't know yet. So we are still trying to model these kind of species. So you can see it's crazy how many species are formed. Okay? So it will take us more effort, I would say, to know all the details, I would say. At this moment, we are still trying to figure out how these molecules by itself break apart. But in future, we would like to know, by having a fuel, by having oxygen, by having a fuel, how these decomposition pathways change. Can we find a system which is even better, I would say? Okay? Are there other species which are better flame retardants? So there's a lot of things which needs to be answered, and a few more. I think it will take a decade to know all the details, I would say. But obviously, Shuyu has a lot of challenge at this moment to look at all the species. Okay. So this is probably almost the last slide I'm trying to show you guys, I would say. So the condensed phase and gas phase, we talked about it in detail, I would say. Huh? What I try to tell people is that phosphorus as a flame retardant work in condensed or in gas phase depending on the polymer. You have to know, a cellulose, or if you have wool, I would say, if you have a lot of hydroxy-containing polymer, the flame retardant will work primarily in condensed phase, okay, the phosphorus. But if you have polyolefins, polyesters, the flame retardant probably primarily will work in the gas phase, the same flame retardant, I would say. But then something which I really didn't talk about is more or less a flame retardant working in both phase, condensed and gas phase. Okay? So they all depend on the polymer. So depending on the chemistry of the polymer, a flame retardant works either in condensed phase or in gas phase. Okay? However, it can also work both in condensed and gas phase depending on some polyester polymers like polyester polyamides. You can see when you burn a polyester, there is a lot of dripping happening. Okay? When you have really burned a polyester. And the drips can be enhanced by adding a flame retardant. Okay? Which the drips may not be flammable, but there is a lot of drips which are formed. And that's because of a limited condensed phase activity. That means what is happening is the polyester is being cleaved into smaller fragments which drip away from the polymer itself. Okay? But you don't see any char, but you see a lot of drips. Doesn't mean that there is no condensed phase activity. There is some condensed phase activity. Okay? But however, it's very complex. I mean, trying to simplify the activity of a flame retardant is very, very complex. It's not easy to simplify all the detail. Each situation is quite different. Okay? That's what I'm trying to say. So each specific system is very, very unique, I would say, and we have to understand the system very, very carefully, okay, depending on the polymer, I would say. So one has to really know what there's a lot of physics involved in the burning process, which we chemists try to avoid discussing. But obviously, we need to discuss together as a physicist with the material scientists, physicists, and try to see the diffusion of additive out of the polymer, how it diffuses out, how it interacts with the flame. There's a lot of physical questions need to be answered. But what we are trying to do is just looking at the chemistry, okay? But the whole process is quite complex, I would say. So, condensed phase, what I try to say is a little bit easier to characterize. You put it on a polymer, You burn it, you see a lot of char form, that's condensed phase, for sure. There is definitely condensed phase happening. But gas phase, really to characterize the specific species which is responsible for gas phase activity is very, very difficult to, or challenging to understand. Okay? So, I hope with time and with few more decades of research we are able to understand things much better, I would say. I would like to thank my small group, I would say. It's quite a young group, I would say. Shu is here. Shu is a visiting student in our team. I don't think she is there in the picture yet. But that was taken a long time back. So it's quite interesting. I learn from these young people, I would say. A lot of this work I have shown here is not my own idea. A lot of these ideas, Shuyu came up with this gas phase activity. We had a few more postdocs who have left my group and were new postdocs. They come up with new ideas how to analyze things. So it's because of the teamwork we're able to handle and propose new ideas to the scientific community. Obviously, a lot of my projects are from industrial partners. You can see a lot of these industrial partners have funded my project. Some of them are governmental organizations which we collaborate with. Shuyu at this moment is doing a PhD with University of Zurich and PSI together. It's a three-way PhD. So you can see, and I also like to thank COST for their support to have you guys come over, I would say, and also us come over and try to discuss the new nice science we do. Obviously, I also like to thank EMPA for this nice building where we get inspired to do nice research. It's really how it looks like in the evening, I would say, when you come. And it's one of the reasons I joined EMPA a long time back, I would say. Still one of the reasons why I still work. So yeah, if you have any questions, I know it's a lot of chemistry, but I hope I could drive some message through you guys, I would say. So send me an email, or if you have any question, feel free to ask, I would say.
Thank you for the presentation, it was very interesting. I was thinking, you were talking about the condensed phase, gas phase, and now this dual mechanism, and also the possibility of having limited condensed phase in some polymers.
Mm-hmm.
It can happen then that when you add some phosphorus flame retardant to a polymer, you have you diminish the result in some specific standard when you characterize it following the standards, because sometimes it's taken into account maybe a lot of melting, and then with this catalysis you are increasing the melting.
Mm-hmm.
Do you know that happens, or?
Yeah, so something I did not talk about in this presentation is we have seen when we develop new additive for polyurethane, I would say, we're able to pass the test very easily, the UL94 test. And we realized that the drips which are being formed are quite different when you add a flame retardant. Sometimes you have, there are a lot of drips which are formed, but some of these drips are not flammable drips. Mm-hmm. They are not flaming drips. So it's a very complex process, I would say. The whole flame inhibition process is quite complex, I would say. Sometimes I struggle to even come up with some explanation, but it's quite complex, I would say. So the physical processes which are involved, like cooling off. So when you have an additive which is present in a polymer, it comes out from the polymer, it takes the heat away from the polymer, so it cools the polymer to some extent. So that's something people ignore, but that's something which is happening. Okay, but also the fact that the chemistry of oxidation or pyrolysis at the surface of polymer could also affect the whole result, I would say. Okay, having a phosphorus flame retardant which is able to volatilize quite easily also makes a big difference. So it's very, very complex. So every system is quite unique, and one should not generalize the whole situation, I would say. You need to really look at the specific situation and try to come up with an answer, I would say. But that explanation may not be valid for other systems. So we really need to be very careful when we come up with a mechanism. Oh yeah, okay, there's a general. It's not general, I would say. We really have to be careful. Yeah.
Just a remark about dripping. In some cases, some investigations should, in some investigation, it should be interesting to analyze the drips.
Yes.
The drops. The drops because it can give some information about the mechanism
Yes.
of fire retardancy and also the way of decomposition of the polymer, because there is oxidation, but there is also chain breakings, and for polyesters it is very important to take into account different mechanisms of degradation.
You're absolutely right, but sometimes I try to be a little bit more simpler by saying that condensed phase is easy to understand. It's actually not really easy. So when you have a char being formed, that doesn't dissolve in anything. So you cannot run a chemical investigation of what exactly is the structure, I mean the chemical structure. You can get some idea, I would say. And when things are happening in a polymer, when it is dripping, is not really what you will see when you collect the drip and then go and look for the chemistry, I would say. Sometimes you're lucky it dissolves in a solvent, so you can run an NMR and you can say, okay, what is the chemistry? But sometimes you really need to freeze the moment what is happening and try to say, okay, that's exactly the chemistry which was happening when the drip was falling. Okay? It's very, very difficult to say. Obviously, we try to generalize, we try to come up with some hypotheses, but it is a difficult, a very challenging topic, I would say, to understand what exactly is happening in the flame. The conditions are completely different for different situations.
You said about PCFC and we're using it for quantifying the gas phase activity, but how does it, can it quantify gas
I
phase?
believe Professor Cuesta is going to talk about it later. Huh? I really appreciate what they have done. Not only them, there are other groups in I think in US who have worked on how to use that tool to quantify the differences between gas phase activity. Probably Professor Cuesta is going to also talk about the chemistry a little bit, I would say, by using FTIR as a hyphenated technique to look at how you can explain some chemistry happening.
Yeah. And then this molecular beam that you said, can you explain a little bit more?
Yes. So when you have a polymer, okay, let me explain now. Yeah. So you have a polymer here, okay? When it breaks apart, it releases a lot of species, but the species see each other.
Yeah.
So you have secondary reactions happening. I'm not interested in those species. I'm interested in what is really being formed. The only way you can do it is form a molecular beam. So how do you make a molecular beam? So if you look at the pyrolyzer here, this is actually the pyrolyzer. It's actually a heater. The molecules are coming from that end, going through. Is that correct? Yeah. Okay. So the molecules are flying through this heated zone, and basically you go from 10 to the power minus 4 to a 10 to the power minus 6 zone. So when they come out, they are expanded. Okay, and expanded in the sense you have a much larger vacuum sitting in the ionization surge. So you are not letting the species which are formed interact with each other. So you're freezing the reaction. Okay, that's the molecular beam. And that's the key, because we really want to know exactly, we need to freeze the molecules or the species which are formed right when it is decomposing. Okay, sometimes the rate of the splitting apart is very, very, very high. Means it takes, I don't know, very fraction of millisecond. You might have some secondary reactions, which we cannot avoid. Okay, but when we make a molecular beam, we are able to see most of the species. Really a lot of these species.
So it's not possible to make. You said species are flying inside the heater, so it is laser heater, isn't it?
No, so what is here is you heat up the pyrolyzer. So really, it's a heating up. So you just heats up. It provides the heat, and when the molecule is flying through this tube, it sees the heat. It splits apart into species, different species, and then when it splits apart, I would say it goes into the ionizing source. I would say, which is okay. So it splits apart here, molecular beam, and then there's a source, or there's a photoionization. So basically, neutral species are not easy to identify. Okay, they don't fly in a mass spec. So you need to ionize it, and that's the key. So what we do is we use photons from the synchrotron to ionize it. The fact that these photons are very, very accurately controlled, the energy of each photon. It's very intense, and we can really accurately control the energy. Means there are, you know, when you split molecules apart, you form isomers as well. Okay, and these isomers do not have a lot of difference in energy. And to be able to see that, we really need a very accurate way of putting energy on it, and that we do it using our optics. There are very nice optics here. We are able to resolve the energy. The energy is 10 to the minus 4 electron volt. So we really can accurately control. Okay.
Yeah, the thing is, the reason I asked was, you know, these sophisticated instruments are not available everywhere. I was just thinking maybe if you have the molecular wave and molecular beam, then for instance, using IR or something doesn't.
No, but
work,
then you have to understand.
Some isomer can be distinctive.
No, you can't even see anything in IR. In IR, what happens is the molecules will meet each other, and then you would not see the reactive species. Okay. So the key is to be able to identify the unstable species, which are really responsible in the gas phase. And these radicals which are forming, they are very short-lived. They will interact with the other species immediately when they see something. So the only way you can do it is really freeze them. The only way is to make a molecular beam. And make a molecular beam, freeze them, ionize them, and then put them into mass spec, and the electron is ejected into the spectrometer. So you map the energy of the electron. So you know exactly mass, electron, you know exactly what species are being formed. Yeah, I mean, it's very simple, but it takes a lot of time. We measure for 7 days, we analyze for 1 year.
Yeah.
That's how it is, I would say. Yeah.
Thank you. I think, as usual, we are with a bit of delay.
Yes.
Just one question, last question, and then we'll go to the coffee break.
Okay, at the beginning you had to talk about condensation phase.
Yes, condensed phase.
And then you said that large molecules, in the case of phosphonate or other phosphate compounds. Okay. During the curing stage, it is some condensation of molecules. If you cure this, in the case of cotton, and you treat it with phosphonate, the classic one or some you develop there. But during the curing stage, you have the condensation of molecules with cotton. It fractionizes. It means there are some reaction between phosphonate and cotton, and there you have the condensation of molecules.
Yes, you're right. So in a normal treatment for cellulose or cotton, you react the molecule with the cellulose, so they are bonded to each other, more or less. Okay, and then eventually when you have a fire, it immediately reacts with, and that's the reason why this molecule which I showed you, HDPP, is very, very effective as a flame retardant. It is a small molecule. It is able to decompose to produce acids quite easily. Easily, yeah.
Okay. Usually those flame retardant compounds decomposes at temperatures higher than the temperature of condensation. That was the
That's good.
Thank you very much.